Okay, yeah, so today, a little different kind of topic. We are going to go through the recent history of one of the fastest growing parts of the design business and even of the infrastructure for semiconductor support, and that is embedded software. I believe this is one of the major factors that will change dramatically the EDA industry in the very near future. If we look back at the history of the semiconductor industry, each decade has been driven by a major kind of change or force. The 60s and early 70s, the mil-aero business is where discretes and other SSI logic made its place, and those were the people who would pay the high prices, and they drove much of the development. In the 80s, microprocessors became the driving force. And in the next decade, the 90s, embedded processors for systems on a chip, so that some of the companies that missed out on the microprocessor era, like TI and ST, for example, made it back in the SoC wave. We had converged technology, computing, and communications in the next decade, and a whole variety of complex chips that blurred the distinction between computing, communications, and consumer products. And today, most people would say we are moving into the Internet of Things, the complex networks that can connect together both sensors and people, and with the computation. Well, for each of these eras, there has been a growing need for embedded software. Now, when we shipped transistors and TTL and discrete logic, we didn't ship any software with it. The semiconductor people simply produced components. But as microprocessors emerged in the 1970s, at least you needed an assembler. Bit slices were shipped. There was basic but very limited software from the semiconductor vendors. But with the microprocessor era in the 1980s, we had an emergence of the embedded software industry. The 68K was supported with Vertex from Ready Systems, which ultimately, through acquisition, became part of Mentor Graphics. But the whole decade was a decade of moving toward more openness, the introduction of Unix in workstations and elsewhere, and the evolution of proprietary real-time operating systems. The next decade, semiconductor manufacturers had to make serious investments in embedded software. And the embedded SoC companies that put DSPs on a chip, for example, now were acknowledging that they had 1,000 or more embedded software developers just to do the infrastructure required to support the design of their chips. And we had in this era rapid growth of the real-time operating system companies, Wind River, Green Hills, Microtech, and it was during this era that Mentor acquired the largest of those three, Microtech. But we also had an evolution of special purpose RTOSes. QNX, for example, focused on the automotive industry and ultimately acquired by RIM. ATI, which was the first royalty-free one, and actually numerically is the largest unit volume RTOS ever produced because it ended up in more than half of the cell phones. The next generation, we saw a clear move to open OSs, and we saw the evolution of Linux as the basis for real-time operating systems. The proprietary ones didn't go away. Certainly, there are still a lot of them supporting the industry, but ones like Symbian were dying out in favor of ones like Android and the emergence of Linux-based real-time operating systems. And so this move into openness has continued. In recent times, it's become clear that operating systems like Android, like Linux, are in fact going to be the drivers for this next decade of the Internet of Things. At the same time, there's been an explosion in the requirements for development of the software that runs on those chips. If you just look back a decade or so at the developments of the most sophisticated avionics in the world, it was not uncommon to have 5 or 6 million lines of code embedded in the particular system. Today, a premium car is not unusual to have 100 million lines of code, an enormous increase, and it's not just the development of all that software, it's how do you maintain it and verify it and support it over time. Well, Handel Jones of IBS has done studies where he queries semiconductor developers and manufacturers and asks them about the makeup of their design teams working on chips, and then divides them into which ones are predominantly software developers and which ones are predominantly hardware developers. And while this part of the curve is his forecast, which says we'll see about a 17x increase in the 6 generations that we've experienced over the last 15 years, the actuals indicate about a tripling in 3 generations of the number of software people on a typical complex chip design, and similar studies indicate the ratios have continued to scale up so that now software people in a chip development project represent 40 or 50% of the average team, and in some cases, even the majority. Well, consider the role of the semiconductor company. At one time, they were providing very little of the software that went around their semiconductor products. Today, whoever develops the core IP, an ARM for example, develops with it a whole set of software utilities, compilers, debuggers, bootloaders, drivers, some type of operating system, and some middleware. The semiconductor SoC supplier takes all that and then redevelops most of it using some of the middleware and OS and drivers, but in general developing this whole set of software utilities for their customers to use in development. But it doesn't stop there. If you're really doing SoC embedded processors, you also develop a reference platform. And that reference platform, yet again, requires a set of customer usable capabilities that have to be developed and supported. And it's not uncommon in the last decade to have an SoC company that ships a new SoC, say for video processing or audio processing, and some of the customers will take the reference design directly and just wrap plastic around it and sell the end product. Most of them will add some value, but they take the basic software and they add application software and in some cases middleware and other things to produce the final product, which is a complex interaction of embedded software with hardware. If you look at the time it takes to do that, it's hard to get a specific measure, but if you just go back to when ARM announces a processor, such as the Cortex A7, to when MediaTek designs it into a chip, to when TCL, one of the larger volume Chinese producers, gets it out in a cell phone, you see it's at least an 18-month process, and even that has a fair amount of overlap between December and February. Obviously, the cell phone manufacturer was working with the chip supplier in advance to get the product out. And there's a lot of pressure on this. Cycle times have to be pushed down. If you look at other cases, also difficult to measure because the Cortex A9 has been introduced in so many forms so many times. But if you take the quad processor and look at what it took for Samsung to embed it and get it in its Exynos chipset, offer a development platform, then work with their cell phone group and get the product out, again, in this 18-month time frame. The problem, of course, is that that is not highly predictable. It's quite uncertain, in fact, whether you will get the product out in time because there are all these people developing those pieces of the embedded solution and redeveloping it along the way. And in fact, if you look at the survey data of people who manage development projects that focus on embedded software for new chip designs or new systems, 60% roughly say that their development schedules are either late or canceled, and only 36% say they are on schedule. Now, I've been told that this data can be interpreted in a different way, which is that 60% are behind schedule and 36% are liars. Whichever, the problem is that the two have to come together, and almost always when embedded software is tested with hardware, new problems arise. Well, that's really the focus that Mentor had in 1995 when we rolled out our integrated system design strategy. It was, I think, probably the first in the EDA industry, and it may have been a bit premature, but we stuck with it. And the basic thesis was that most of the system design problems, delays, and schedule issues occur when hardware and software are integrated. And if you could give a virtual representation of the hardware design to the software developer early in the cycle, you could minimize those integration problems and, in fact, get a jump start on the software development. And for most chip designs, there wasn't that much embedded software in 1995, so this wasn't yet that much of a crisis. And so a lot of the interest in this strategy came from systems companies who were integrating hardware and software. But the chip design people actually did latch onto it, and we produced some successes. Probably the most significant was Seamless, which certainly for its time was by far the most successful hardware-software co-design product and co-verification product, may even be today the largest selling, having done $150 million of sales and a peak revenue of about $25 million per year. It was a case where hardware-software co-verification really became a meaningful business. But there was a problem, and we noted this despite some degree of success. We noted that the people who were buying this product were basically hardware people who were using embedded software as a stimulus to verify their hardware design. And as we surveyed the customer base, we weren't getting any embedded software developers buying the product, and yet they had been, we thought, a primary target for this kind of product. So we continued to develop products that would bring to the embedded software developer the things they needed from the hardware environment, and sort of a hybrid environment or tool to develop things. And we did this with a number of different products. Unfortunately, the embedded software developers are very different people from hardware designers, so the products really didn't stick. But in 2002, we thought we had hit the formula with a product called ASAP. Actually, the original creator is here today. And this product was something where there was demonstrable benefit to both the hardware and software groups. And the thing that really got us excited was a major, actually one of the largest consumer products companies in the world, had a problem that we were able to solve. And their problem was they had a chip they were developing, and actually an ASIC with an embedded processor that had to go in a portable application. And the processor was burning 8.4 milliwatts, and they had to get to 4.5 milliwatts to achieve the battery life that they wanted to commit to their customers. And they had a team of engineers, 3 engineers had worked full-time for an entire year, and they had gotten it down to 6.5 milliwatts. And on our first visit to the customer, right there in front of them, we used the product to demonstrate how they could get to 4 milliwatts. And the way the product worked was this. They had a processor that was running, 0.1 milliwatts per megahertz, and so they were running at 77 megahertz. And the product does analyzes the embedded code, looks at the threads of execution, and finds where the bottlenecks are. And then when there are bottlenecks that are identified, synthesizes hardware to replace software to achieve more efficient execution. So in this particular case, they synthesized a number of hardware blocks, and as a result, they could cut the frequency in half, and they therefore reduced the CPU power consumption proportionately. And so all of a sudden, this difficult task of getting below 4.5 milliwatts was achieved. Now, in this case, we asked the customer for the design just as it existed 1 year before when they were at 8 milliwatts, and in one day synthesized the blocks of hardware required and sent it back to them, showed them here's 4 milliwatts, and they were absolutely ecstatic, as was our sales force. So everybody was delighted. Here we knew we hit a home run because we had just taken 3 years of work, compressed it into a single day. They had achieved their goals. We were delighted. We're waiting for the $1 million order. Our salespeople are waiting for their bonuses, their trips to Tahiti. Everybody is high-fiving it. It's really great. And I keep asking, when are we going to get the order? And, a strange thing happened. The customer went radio silent. They stopped responding to our inquiries. And people began to get a little troubled because we thought that success was imminent. And about 6 months later, it became apparent that they could not figure out how to buy and deploy this product. They couldn't decide among themselves, the hardware group and the software group, who would be responsible. And the basic attitudes internally were the hardware people saying, no software guy is going to synthesize a single gate in my design, and the software people saying, no hardware designer is going to alter a single line of code in my embedded software. Well, you think this is pretty childish, and surely they work through this. This is very serious stuff. Sociology is far more important than technology in the adoption of new technology. And so, amazingly, after a long period of time, they actually decided that they couldn't adopt it. They couldn't settle the argument. They agreed that the results were miraculous. They agreed they needed it, and they said, honestly, we cannot use it. Sorry, we're not going to buy it. Well, this was quite a setback. It turns out they were not unique. There were a lot of other people like that. And so we investigated this further, and what we found is it wasn't just the issue of hardware versus software at the product level. The reason that the embedded software people were not buying our Seamless product was the whole infrastructure. So for example, for the Seamless product, it sold for $50,000. The hardware people said, gee, that's a good deal, EDA product, $50,000. The software people, when we had a special version for them that went for $1,000, they said impossibly expensive, can't do it. And not only that, their expectations were different. The kind of support they expected, the downloadability, everything was different from EDA. So this simple transition that I envision, where an EDA company that helps people design hardware would also help them develop, debug, and ship the embedded software, turned out we were dealing with two dramatically different cultures. And to please both with the same product was not possible. It's just, it took us a while to learn that. Another thing that the world still seems to not have learned is that people develop expertise and ways of using computers to develop their products, and changing that user interface is a very serious issue. What you have to do is bring the information they need from other domains to be system aware, but they will demand their own. And I frequently get inquiries from people, why don't you merge with a hardware company and you can offer hardware design along with electrical design, or embedded software along with hardware, or system design along with chip design, and so on. And the fact is that people don't want hybrid environments. They will reject them. What they need is the limited amount of information that affects them, and they need it in the format of which they're used to using. So the challenge is, how do you get a user environment for embedded software people that provides the information they need from a virtual hardware design, but does it in a way that treats them as embedded software people, that allows them to work in the way they become accustomed to. Well, we took a long path to get here, but the way you do this is you have to think like an embedded software person, you have to act like one, you have to go and talk, and they need to feel this is an embedded software company, not an EDA company, because I don't like EDA companies. So what we did was we started acquiring embedded software companies, starting with Microtech, I mentioned, which at the time was the largest of the embedded software companies. And then in the early part of the last decade, we acquired ATI, Accelerated Technology, which had Nucleus, which, as I mentioned, in unit volume was the largest selling RTOS. Unfortunately, because it was royalty-free, it was not the largest selling in terms of dollars, but certainly connected us with a lot of applications. With the acquisition of Embedded Alley, services came into the picture, and particularly support of Android and Linux. And the move to open source was accelerated as Code Sorcery joined us, and premium services came with that really now brought the company so that embedded software people were no longer a persecuted minority. They were, in fact, an entity of the company that represented a substantial portion of our revenue, and in fact could be embedded software people in an environment that didn't start out as embedded software. Most recent one we announced in December was the acquisition from Cavium of what was the Monta Vista embedded software business for automotive, a major thrust for us. So Monta Vista was really the pioneer in Linux, RTOS for applications, especially focusing on an open software world. And in fact, that now is part of Mentor. And with all this, even as you become an embedded software company, you have to adopt the whole culture. And if you want to be on the leading edge of embedded software, that means the whole open source community. And that, in fact, is what has evolved in the Mentor embedded business. And you may think of open source as sort of anarchy and chaos, but in fact, it really is a very well-structured, well-defined kind of operation. So the people in the embedded source community have organized projects, dozens of them going on at any one time. Peers select the leaders, and so it's a meritocracy. Those who are the best contributors over time are respected by their peers, and they move up into positions in charge of projects, and they become reviewers and committers. And if you look at Mentor Graphics, probably as large or larger selection of top-tier embedded software people in the open source community of any company today. The very top levels of people who are actually authorized to release to the embedded software threads and the development of the compilers, debuggers, the whole open source infrastructure of products. So today, Mentor has over 50 people involved at all levels, including the top levels. Well, the dream, of course, is if an embedded software can develop in his or her own environment and not really care what's underneath, then you've solved the problem. So does it really matter that that embedded software developer who is used to dealing with pre-production prototypes or even production parts, and so has always focused here, what if you could plug in a virtual representation instead? An emulation, for example, or even a high-level model like a System C model that can execute as rapidly as an emulation or even a prototype. Well, what you need is, first, a widely accepted embedded software development environment, and second, the ability to connect seamlessly to all of these other virtual representations. Well, we have that development environment. Sorcery Codebench over the years and its evolution both before and since it's become part of Mentor is probably the most widely accepted preferred solution for embedded software developers, particularly in semiconductor companies. It's based on open source. That's another reason we have so many open source people. GNU compiler, or GCC, debugger, libraries, QEMU simulation. So embedded software developers want QEMU models. You tell them that, oh, we do TLM 2.0 models. That doesn't ring well. And so you have to become the software developer. Today, Sorcery Code Bench gets about 15,000 downloads a month. Typically, annually, historically, it's been 150,000 downloads a year, and 300 releases. This is the way the embedded software community works. This is what you have to become if you're an EDA company and you want to be successful providing embedded software development tools for your entire development environment. And so, the next element in that solution is what we are going to call Sorcery Code Bench Virtual Edition. This is the portion that is embargoed. And this will be introduced by Glenn Perry, who is the general manager of the embedded software division of Mentor Graphics. And this is what takes us to that next generation of development environments for semiconductor companies.
Thank you, Wally. Thank you. You mic'd up? Great. Well, thank you, Wally. That was a great introduction, and thanks everyone for being here today. I am really excited about this announcement. I've been at Mentor since 1999, and with the exception of the last 4 years, my time was spent on the hardware side of the equation. And so some of the learnings that Wally talked about here today, I quickly discovered firsthand when I moved into the embedded software space. And so it's taken some time to really comprehend the importance of having a solution that's designed for an embedded software developer to enable embedded software development throughout the entire design flow. And one of the things that you'll note in this integration is that we're able to take our own platform, the Sorcery Code Bench platform, because Mentor is not only an EDA, because we are also deeply invested into embedded software, we actually have an embedded software development platform called Code Bench that we can modify in significant depth to integrate these other design representations in a way that looks just like the original embedded software development environment to the embedded developer. So one of the things I want to just spend a few minutes to walk through here, and then we're going to do a little demonstration for you, is I'd like to explain how this is applied both pre-silicon and post-silicon. And we'll, again, just one note on the platform for all of this. In the Code Bench environment, you'll notice the sampling of logos here at the bottom. And it's a sampling of some of, but not all of, the semiconductor companies who pay Mentor to build the tool chains for their new processors and for their new SoCs. So no modern SoC goes to market today without a tool chain, compiler, and debugger. And because Mentor is in the business of supplying those in a custom form, that's how we end up with such a broad deployment. The semiconductor companies pay us to customize it, and then we make it available to all of their customers, and we end up with 150,000 downloads a year of this platform in the embedded software community. So having a tool that is the de facto standard is a really key starting point. We were able to take that platform, and for the software engineer, we could extend some of the UI features to make it easy to connect to something like the emulator. We've integrated something called an analyzer. Now, one of the things we joke a little bit about is if you talk to most embedded software developers about a waveform, they get a blank stare on their face because they're not accustomed to a world of waveforms. In a hardware design community, it's perfectly logical to us. These are the kind of fundamental differences that the embedded software development community struggles with when we try to move between the worlds. So we put things like an analyzer environment, which we'll show you in the demonstration, that really transforms data that comes from hardware intelligence that we have in our EDA products, but puts it in a form that the embedded software developers can really understand. That's done through some deep integration in the CodeBench environment. Because we develop it, we can do a great deal of extension to it. We also connect to simulation. Wally mentioned the fact that QEMU is an open source based instruction set simulator as well as peripheral IP model blocks, high performance, untimed. But the traditional simulation, high-level simulation flow for EDA is system CTLM. We're agnostic, realizing that some hardware developers may actually want to use portions of this environment. But in the embedded community, most people prefer QEMU. We have a product called Vista that can be used for the model development. And you'll note that it's a hardware engineer that's going to be doing this model development. And once you have these platforms, and once the software engineer is running on the platform and a problem is discovered, it's not uncommon that the question will come, well, where is the bug? Is it in the software or is it in the hardware? I met with a customer last week who said, you know, we do a lot of things to verify our chips, and we think we've got them verified. We tape them out. We hand the reference board to the software development team. They throw 10 million lines of Linux on it, and they discover functional bugs that we couldn't catch in our test vectors because we just couldn't exercise enough configurations. So it's really important, the point at which the software developer finds the bug, that you can have a snapshot of that exact same run in a hardware-centric environment. So this is our CodeLink Questa UI and Veloce GUI running on top of the emulator. So the design is simultaneously being represented in both CodeBench and in the hardware development environment so that they can both have a native environment to do the debug. A few benefits, starting with virtual prototype. Most people think of virtual prototyping in terms of early access. If I have a model, I can have that before the actual silicon's available. That's absolutely true. In fact, you can use these models before the hardware design is complete. You may discover that there are problems in the interfaces between the hardware and the software. There are some other advantages post-silicon that are less obvious, but I'll mention here in a moment. One of the abilities that you get in the high-level model is to be able to control the hardware in ways that you can't on a physical board. And that turns out to be pretty valuable. If you think about the use cases that people apply at this stage of their design, they want to make sure that the software-hardware interfaces are functionally correct. They're going to do a lot of optimization and development, porting, basically, of the operating system itself, which includes a lot of driver development often, perhaps new drivers for any new hardware acceleration blocks that you have in the platform. So these are typical use cases pre-silicon. What's less obvious is that when you get to post-silicon, a virtual prototype environment or an emulation environment will let you have visibility beyond what you could otherwise see if you had the actual SoC on an evaluation board connected via JTAG probe or trace probe. And I'll give you a little bit of an example of what I mean by that. So this is our CodeBench environment. This is a JTAG probe, and this is a reference board, kind of pictorially described as an SoC here. And what JTAG gives you is it gives you a view into the core, the memory, and the registers. And you can do anything you want in terms of visibility as long as you do it within the core and the memory and the registers. But it turns out there's a lot of other things on this device beyond that. And if you try to reach in and see them through other means, you end up affecting the behavior of the chip, kind of a Heisenberg-type problem. Well, if you're running on a virtual prototype or on an emulation environment, you still get your core, your memory, and your registers, but you also get timing, power, peripheral, behavior. You can go in and figure out what's happening in a peripheral, much more detail, full visibility, and you can do it without impacting the performance of the device. You don't get the Heisenberg-type problem. So this is really valuable, and this is a post-silicon type of operation. A lot of people, you know, the chip's working, but it's not performing at the level they want. They want to understand what they can do to improve that. It's hard to figure that out. In the emulation environment, we're doing some of the very same things, just at the next level of fidelity. So we're doing software debug on the ported OS and the drivers, boot code. We're going to test the hardware and the software in a validation exercise, the emulation is going to run slower than a virtual prototype, so we're limited in how much code you can run through. So you pick the select portions where you need to verify. And we actually find customers do some level of configuration setting at this point. And this is, again, very similar in the virtual prototype world where you're going to be developing the code on a representation of the hardware, but it's a much more accurate representation of the hardware. It's the actual RTL that you're exercising. You, again, get to look into the system performance, as I mentioned in the previous slides, and you can do this in this environment in either an online or an offline mode. So you can run and collect a lot of data and then have several software developers analyze that data offline, or run real time with the emulator as if you were connected to the real board. Once you've got past the emulation and the virtual prototype representations, in the exact same environment that you've used for those, you take the same CodeBench environment, you connect it via JTAG probe to your hardware when your hardware is available. You change a few menu settings and it looks and works exactly the same way. So we've actually got a demo, as I mentioned, that we'd like to show you that kind of highlights a few points of this, and then we'll be available for Q&A. So with that, I'd like to introduce Rick Vilbig and Russ Klein. Rick works in the embedded software group and focuses on our probe integration technology. Russ, as Wally mentioned earlier, was one of our original inventors of the Seamless product, and today works in our emulation team.
Okay, so we recorded this video in advance because it's hard to bring all these configurations down here. What we're going to show you today is the same Sorcery CodeBench virtual edition, integrated development environment, debugging on 3 of the different nodes that Glenn mentioned. First on the Vista virtual prototype, and then on a Veloce emulator, and then lastly on real hardware. So go ahead and play that, or I guess I can. Okay, so this shows the different places you might run your code to debug it or to test it. So we're going to start the demo. We're going to show the virtual prototype, things you can do there. It's the same user interface throughout, but with their special visibility you get at different nodes during the debug process. Then we'll move on to debugging the same code on the same design on an emulator. And then lastly, we'll move to showing this on the real hardware. All right. Okay, so in just a second, this shows what the Sorcery CodeBench IDE looks like, and I'm going to just show a little bit about what the software developers are actually doing. On the right, you can look through what's in your code module and move your viewpoint and edit your code here. And then you can build the code, make sure that all the compiles correctly, and so forth. And then once it's built, we want to be able to debug it on any of these different platforms, a virtual prototype or a Veloce emulation, an FPGA prototype or a real prototype. And so you can just pick which type of target you want to debug against now. So here's the virtual platform we're going to run this code on. So as we're going along, we're just able to single step through the code and see registers and memory in the upper right window. As we're stepping along, we can see things are changing. And so what I'm doing here is just stepping through some test code. We have some test code that is sending data packets through a FIFO, which is in loopback mode, so we can read the data coming back through the FIFO and compare it. So we're going through, and we've done a simple test of 10 bytes each. I apologize, it's hard to see the screen because of resolution stuff, but I think you have a copy of this video on your USB stick, so you can look at it later. Anyways, then we move on to a longer packet test where the packet exceeds the FIFO size, and we've sent 66 bytes through there. But when we tried to receive it, we discovered that something didn't work right. And so it turns out there's a software bug here. I created a software bug. So now I'm going to go fix it. Unfortunately, somewhere off the left side of the screen here is where I'm fixing the code. I'm just editing the source code to fix a mistake. Then I'm going to rebuild it by just clicking the debug button again and bringing up the same debug environment with the new code base. Okay, and some things are going off on the left side of the screen here, but so I'm selecting my debugger, and that restarts the simulation run and restarts the debugger, and then I can start debugging through my code. So this is a very typical daily life for a software developer. Writing your code, rebuilding it, and stepping through and looking for more problems, or you're probably really looking to make sure it works right, but you're finding that there are problems. So this time I went through the quick test and it worked, and now I'm stepping through the longer test, and this time it worked. So I fixed my software bug, and that's looking good. After that, I run through a loop, sending a lot of random data size packets full of random data through to exercise it a bit more thoroughly. So you can see how debugging the software here early like this is going to help your schedule. But when you're using a Vista Virtual Prototype, you also get some unique views into what's going on in the system. As Glenn was saying, you can, as the simulation is running, it's recording, for example, power consumption levels. And we can correlate this back to the code. So you can see when there's interesting things happening on your power consumption, then you can find out where in the code were you at that time. What was your code actually doing? And we should be getting there any second here. And one of the important points is the instrumentation that we need to capture that information is done non-intrusively, completely. So you don't have to modify your code to put in test hooks or anything like that. So this curve is showing the power as the power is going up and down. And in the demo, what I did was I then went and optimized the code, and now I can bring up in two screens side by side to show my power in the first session was 117 something milliwatts. After an optimization pass, I was able to get it down to 100 milliwatts. So that shows how you can really start analyzing the system behavior and performance before you've even finished the hardware design, while you still have a chance to make some changes.
Okay, next we'll be running that same design, but we're going to run it on a representation of the design that's not a virtual prototype, but is an emulation of the RTL. So we've taken the RTL, compiled it, downloaded it to the emulator, and when we launched this configuration, it initiated a session down on the emulator where we're going to run through the same tests that we did in Rick's example on the virtual prototype. Here we're running some simple tests against our FIFO. It's a little off to the right, you can't see it. And then we're running through some larger tests, and that works well. We can see registers, we can see memory, we can see variables. The software developers have the exact environment that they're used to all the time. And then when we run our large set of random data, we find out something's not working right. And at that point we go in, we can look at the registers, not just in the processor itself, but we can actually look at registers out through the RTL down in the emulation system without going and learning some complex EDA tools. What we find out is that our empty bit is stuck, and that's when we go and get the hardware team and say, hey, you might want to go take a look at this because we're seeing the hardware really not respond the way we think it should by actually looking in at the registers in the hardware. And the hardware team can come in now and they can bring up the waveforms and correlate what was taking place over in the software with what was taking place on the hardware. And we can see here off to the left side, we've got the FIFO working. On the right, it seems to wedge. The hardware guy can go in and take a look at all of the data that was collected on the emulation. He's got full visibility into what's going on. But the software guy can lead him to this problem, which would have been very difficult to uncover purely in a hardware verification context. And so they can then go in and identify, oh, what we find is that there was an interrupt that occurred when the FIFO was full, and on that particular combination, it causes the FIFO to lock up. We've got a reference to the FIFO there. And so we can then go out to the RTL. The hardware guy can fix that by increasing the size of one of the registers. And by doing that, we find out one of the registers was too small. We can increase the size, recompile it, re-download it to the emulator, and then we can go ahead and rerun that test and make sure everything's working correctly. So again, the software person has his traditional environment to be able to run against. He can download, he can initiate an emulation session from the cockpit that he's used to. He's just connecting to a different target. There's really no difference in what he does from that point to connect to the target. And now we can run that fixed RTL. We can run the same program against it, and we can observe that everything's working correctly.
All right, so then the project progresses a little bit. You know, we've done our functional debug on the virtual prototype and on Veloce as well. We've done some system analysis and power analysis and things. And the project moves forward, and we're actually going to build some boards now. Okay, right. So this is a picture of the Veloce box that Russ was debugging on. So then we move forward, we have our board, and we connect up a JTAG probe to it. We've already done a lot of our debugging, and besides debugging the code, we've developed our test infrastructure, our QA test procedures, and things like that. So when we get our board back, we're on the same exact debugger, except we picked a JTAG probe to connect to the physical board, and we go through the same exact debug environment again. But now, when the board comes back, we have all the code is written, the test infrastructure, QA, test suites, all those things are in place, and we can just test the final board in the real system, in the real world system, instead of starting our development when the board gets back, or at least starting our debug when the board gets back. And so this really helps advance the schedule and also results in a better quality, because you can fix hardware bugs that are found before the design is finalized, and so that's it. Any questions, or a couple minutes?
Do we have questions here?
Who is buying this new code bench system? Is it the software people, or is it the hardware people?
So the CodeBench Virtual Edition that we've shown you here today is targeted for the software developer. So it's the environment, CodeBench Virtual Edition, is really designed for the software developer. It works seamlessly with our hardware design tools and flows. So it's quite typical that a software developer in the CodeBench Virtual Edition will discover a problem and be able to hand it off to a hardware engineer, but the hardware engineer will debug it, as Russ was demonstrating, in the native hardware development environment.
So the software and the hardware people, they work with the same GUI?
They do not. And in fact, it's really a key point, is that we, in our history of over a decade of trying to get a GUI that was loved by both hardware and software developers, we concluded that that's not possible. That if you try to take a hardware design tool and morph it so that a software developer will use it, it will be below their expectations. It will have things in it that the software engineer does not understand, and he will not use it. And we've had this experience time and time again. We've learned a lot of lessons in that space. That's why we thought it was so important to take the native software development environment and make it more intelligent, because that's what's familiar to the software development community. A hardware developer, in a similar sense, there are all kinds of things in the native software tool that are not familiar to a hardware developer. So he'll want to work in his environment as well.
So do you actually make money through the software developers directly, or is this sort of play essentially that by tying this all together, you kind of actually get your money on the hardware side?
You want that, or shall I? Okay. We do, but we do it in different ways. In fact, it's our business models and the end users and even the purchasing agents are sufficiently different that we actually have an independent sales channel that addresses the embedded software community versus the EDA and hardware community. The price points are different, but the volumes are different. You're talking about 10x to 100x, minimally 2x the number of software developers, depending upon how high you go into the stack. So the economics work, but you have to run it as an embedded software business. And you can't, I think it's virtually impossible to try to have it be a small side effect of your hardware design business. You have to really invest. Mm-hmm.
I would also add that the embedded software business at Mentor Graphics is a profitable business. It is one of our most rapidly growing businesses. And what's even more remarkable is that the open source services we provide, that is the things that Glenn talked about in providing customers customizations of basic open source tools, is our most profitable service business within the company, approaching levels of margins that are somewhere in between emulation and software itself.
Yeah, I wanted to ask, so Glenn, with the system that you had up there, is that everything, or do again the developers have to go get some software from someplace else and some other bits and pieces? And kind of the opposite question, if they decide to buy, piece number 1 and then do something else for piece number 2, are you gonna do it that way as well? You know what I'm saying?
I think I understand the question. I'll try to answer. If I got it right, is the environment we're providing the software and developer everything that he or she needs to do the type of development that we described here? The answer to that is yes, but I guess it's a qualified yes. Because when you think about what does a software developer really need? Well, they need if you recall the slides that Wally showed where from the IP supplier to the SoC to the system companies, the buildup of the software stack and tools that go with that. So we supply the tools. We also supply operating systems. But a software developer or a company may want to use an operating system from another company. And if they choose to do that, they can use that directly in our environment. We certainly have no issue with that. The tool's designed to do that. So we obviously can't supply all the software that anyone could ever use, but we supply the tools that will digest and let you debug and develop in this manner any software that you put into it.
So you figured out how to solve the hardware-software conundrum here. What's next? And what's next in context of the things that I hear Intel and others saying about, we have to now design for the end user, the end consumer experience or use. And by that, they seem to mean that kind of input is going to affect the software, certainly, but is even going to affect the hardware before it's finished. So what's next?
Well, I actually think that the first steps are perhaps less revolutionary than you would think, because I think we underestimate the large differences in the disciplines between computer science and electrical engineering. And most electrical engineers have had some level of computer science in their training, but most computer science experts have not had hardware design expertise. So we've got a big hill to climb to get just our software community aware of the impact and improvement they can have on the overall system. And I'll give you an example. When I moved into the embedded business at Mentor, prior to that, I'd been working on power optimization using high-level System C models. And at that time, a semiconductor company, you could have a meeting with any C-level executive if you had a solution that could trim a few percent of power off of one of their designs, a few percent. I moved over to the software group and started looking at some of the examples of what was being done in the code in implementation on the embedded side, and realized that tens of percent of power were just being destroyed in the software implementation. And I thought, man, this is a gold mine. We've got this. All we have to do is show the software developer their problem from a power perspective. And our first attempt at doing that, they said, we don't understand watts and joules and power. That's not our problem. That's a hardware problem. We later went back and reworked our solution and came up with something that gave them things like remaining battery life and gave them things like peripheral state is in particular suspend or deep sleep. These are things that display as at X percentage. They're fairly basic things from many hardware designers' perspective, but the complexity that the software developer deals with on the software side is huge. Picking up some of this hardware understanding is a big deal. So I think the next step is we see more companies picking up, more users picking up this flow. The awareness in the software development community of their impact on the overall design is going to go up dramatically. Yes?
I want to know the scalability of this platform.
Scalability?
Yeah.
That's a good question. So I guess I can, I mentioned in the virtual prototypes, the KIMU models or System C models if you like, that you can write those in varying degrees of fidelity. So you can have a model that has no timing. It's just a functional model. It runs as fast as hardware, real hardware. And in that sense, there's no real inherent limit on scalability. At the same time, if you want to see detailed, very detailed timing and power, you're going to have a performance impact to try to run a simulation platform with that much fidelity. So we give the users the knob to turn in deciding how much or how little fidelity they need, and with that, how fast or how slow the model or virtual representation can work. Now we have people on our emulators that are running their full chip, full SoC. We also have companies who run specific blocks of IP off of the SoC. And there the question becomes, how much software do you need to drive through the emulator in order to sufficiently exercise it? So it really comes down to a timing question of how many emulators are in place and in that environment, or how much fidelity you need on the virtual platform, and how much software you're going to try to run through it. But I would say we've given customers and users some big knobs to turn to go anywhere from very fast and everything you could imagine in size to very high fidelity and a smaller subset of the total design.
Did you include the best practices for software engineers to reduce power loss?
To reduce what? Well, power loss. I would say this is a work in progress, because the problem isn't in one place. The power problem isn't in one place from the software development perspective. We have put solutions in this environment to make the software developer aware of how they're impacting power in a way that they can understand. We've added frameworks, power management frameworks, into our operating system to help the customer configure their power utilization more effectively. We've added instrumentation into our operating systems so that they can collect power information and understand what's going on. But it's a collection of pieces, and there's still plenty more to be done. There's no automated best practices at this point. The system doesn't tell you, gee, you could have done this in half the power, changed this and this and this. But the frameworks that we've put in place give us the most important part of that holy grail, which is visibility to what's really going on from the software perspective.
Okay. But
Somebody mentioned something about this being embargoed, but it doesn't say anything on the presentation about what the date is or anything. What's the actual status of that?
I was told that it's embargoed until April 22nd. April 22nd, is that correct? I mean, next Monday. Okay. Okay, gentlemen, thank you very much. And so just a quick housekeeping. We are having a long break today till 3 p.m.